wondering how come some bookcases are so shaky. So we take a look at basic engineering this week. We also got a tour of the world's greatest train set. But first, here's a simple idea that went screwy.
Do you realize that we now have a generation of kids that can operate computers, haven't got a clue which way clockwise is, but know what all the channels in the TV guide are on what cable channels? Gets a little scary, doesn't it? The proliferation and growth of cable TV has been so fast it's hard to keep up. Well, I can't help you remember what channels are on what cable channels, but look at the story from the beginning will at least explain why it's such a mess. Okay, here's a guy who lives in a valley. For the last 3 years he's been watching snow on his set. In actual fact, this is no more boring than what's normally on TV, but he doesn't know that yet. He decides to invest in an antenna at the top of the hill. His neighbor splits the cost of the antenna with him and splits the signal coming from the antenna too. That makes the signal weaker, so they have to buy an amplifier to keep it strong. As is the case with most remote communities, the channels they can get come from several different directions. So, after a few weeks of arguing which way the antenna should point, they invest in more antenna heads, point them in all directions. That increases their investment in antennas and hardware to combine the signals, so they offer the signals to everyone else in the community. Cable TV is born. This is the cable that comes into your house from the cable company. It does the same job as this stuff did in the days when everybody had their own rooftop antennas. It carries signals from the antenna to your set. Flat lead has a problem though. Long lengths of it act just like an antenna too, picking up all sorts of unwanted signals. As a matter of fact, if you have an FM receiver, they probably gave you a piece of flat lead with it to use as an antenna. For large systems with miles of cable, coaxial cable is a must. It's called coaxial because of the way it's built. The signal goes down the center piece of wire, and that's surrounded by a shield. The signals that the cable company are giving you are still broadcast signals, so the shield keeps them from radiating out of the cable, and it keeps unwanted stuff from radiating into the cable. That brings up the first interesting possibility. Originally, when cable started, there were only a few channels being delivered. In order to snazz up the service, cable operators started to supply a community channel on their cables. Inserting a cable channel is only a matter of adding a flea power transmitter at their end. As time went on, cable companies discovered there were all sorts of interesting things they could charge extra for. As long as the cable company has a cable from them to you, there are a lot of other signals they can send. Some come from satellite, especially for cable viewers. Some are produced by the cable company in their own studios. But there's a problem. TV sets were built to tune in 12 VHF channels, 2 through 13. The UHF channels from 14 to 83 can't be sent down this particular cable. If you like bizarre but surprisingly accurate analogies, try blowing real fast through a drinking straw. The higher frequency UHF channels get their energy absorbed by the cable too. To make matters worse, any channels that have strong local stations on them can't be used. People who live close to the transmitters will get interference on those channels. Even if the cable company puts, channel 5 on the cable as channel 5, channel 5 will interfere with itself. I can hear you asking, how does that channel interfere with itself? Well, if a strong local signal is put on the cable on its own channel, the signal from the cable company will arrive at the set at a slightly different time than the direct signal from the transmitter. In the days before cable, this effect would happen with bounce from tall buildings. The effect's the same, a ghost. So we can't use the UHF tuner, and we have to avoid any VHF channels that have strong local transmitters. That leaves us with less than 12 channels to use. The answer is hiding over here on this government chart. If you look at the assignments for who can broadcast on what frequency, there's a great big gap between channel 6 and channel 7. It's big enough to hold 14 channels. There's also a huge gap between channel 13 and channel 14. Now, the signals that the cable company are sending are the same as the ones that are broadcast, but the cable companies are confined to the cable. That allows them to use the same frequencies that are occupied by aircraft, taxis, and ships. They won't interfere. So that's great. We can now send all sorts of extra channels that couldn't be used in the open air. Now, it's a fairly easy matter to convert any channel to any other channel, but your TV set can't tune them in. So I'll give you one of these. This thing can tune in all the frequencies between 6 and 7 on the dial and convert them to channel 3. So you hook it up and you tune to channel 3. Unless, of course, there's a strong channel 3 in your area, then you use channel 4. With all that converting going on, the cable company has to issue a chart. Now here's what's actually happening. The numbers 2 to 13 on the converter are the real channels 2 to 13. The cable company has reconverted some UHF channels in your area to these, and chances are the others are on the wrong channels, but they really are 2 through 13. It's 14 to 60 that aren't what they seem. 14 to 27 or so are the hidden channels between real channel 6 and real channel 7. 28 to 60 are between the real channel 13 and the real channel 14. No wonder they have to publish a chart. Now, if you really want to confuse yourself, think about what happens when you go sequentially up the numbers on the converter. From 2 to 6, the converter's giving you this piece of spectrum. Then it continues on up here for 7 to 13. Then it gets its 14 down here and continues up to about 28 there, and continues on above 28 up here. It's all in an effort, you see, to make things appear simple. Now, you may never need to know all this unless you buy a set that has a tuner like this one. Each one of these little buttons can tune in the whole cable TV band. It's up to you to hunt down your favorite stations and assign them to the buttons. Unfortunately, none of this explains why you can have 60 channels and there's still nothing good to watch. What has 5,000 wheels, 2,500 motors, and takes 150 million people on a 43 million mile trip every year? The Toronto subway system. The world's greatest train set. Years of riding the trains with a nose pressed to the front window didn't help me decode the mysterious signs and signals found in the tunnels. A trip to the training simulator and a tour underneath the trains explained a lot. A lot of the unusual terminology stems from the science of direct current electric motors. Unlike internal combustion engines, electric motors develop full torque from a dead stop. They're direct drive, no clutch, no gear shifting. DC motors also work backwards. If you spin them, they generate electricity. This is one of 2 trucks found under each subway car. It consists of 4 wheels geared to 2 motors. This is power control. The power to operate the trains is divided into sections. Each section is fed from local high-voltage AC power, changed to DC by huge rectifier substations. A loaded train pulling out of a station can draw 10,000 amps at 600 volts. I'll let you figure the wattage. Power control also monitors pumps, emergency lighting and power, stairway and track heating systems, and ventilation fans in the 65 subway stations. The 600-volt supply is fed to each set of motors on the train by a collector shoe that rides on the third rail. The other electrical connection to the train, ground, is made by the wheels. Here, a train is being bugged. That's plugged into 600 volts for service at the car house. Here's a sign we all liked. Under the trains are the motors, heating and cooling equipment, a motor alternator set to provide alternating current for the fluorescent lighting, and a 36-volt battery pack that will run communications and emergency equipment if the train loses power from the third rail. This rubber accordion is a load leveler. That keeps the train level with the platform no matter how many people are on board. There's also an all-important piece of equipment called a traction control box under here. The driver's hand controller controls the traction control box, and the traction control box connects the motors to the 600-volt supply in several ways. The driver has 3 speeds: inch, series, and parallel. Coast is really off. No power, no brakes. In the inch position, the drive motors receive their power through a large pack of resistors. The resistors dissipate most of the power as heat, and the train pulls slowly ahead. In series, each pair of motors on the trucks is wired in electrical series. Each motor has 300 volts applied. You can loosely think of this mode as half power. Parallel is full power. Each individual motor receives 600 volts. That explains the signs in the tunnel, S and P, series and parallel. The signs are color-coded for the different types of trains found on the system. The O is off for all trains. Stopping is accomplished by turning the handle to brake. Most trains use dynamic braking. When they're slowing down, the motors act as generators, converting the train's momentum into heat in the resistor pack underneath the car. Newer trains use regenerative braking. The current's fed back into the third rail to help run other trains. This electric braking fades away as the train comes almost to a stop, and air-operated brake shoes take over. A brake pipe connects all of the cars together. The system's set up so that losing pressure in the brake pipe will apply the brakes. Several things will do this. One is the driver coming into a station. Another is the emergency stop handle. Another is the driver taking his hand off the controller for any reason. And still another is a small trip arm at the front of the train. The last situation will happen automatically if the train passes a red signal. Running past a red light not only blows the brake pipe, but causes a lot of paperwork. The signal lights seem a little confusing at first, but they make sense if they're taken one at a time. An amber means that the next signal is red. A white signal indicates that if the proper speed is maintained, the next red signal will change when the train gets there. Green is go at authorized speed. At places where there are branches off the main line, a bigger stack of signals is used. The top three lights refer to the main line. The lights below refer to the route that the train will take, how the track switches are set. This is designated speed, top green, over the main line, bottom green. This is caution, top amber, over the secondary route, middle amber. There are various other combinations. This is transit control. Theoretically, because of careful choreography, the system could run itself without this room. But with 88 trains running on the system in rush hour, spaced about 2 minutes apart, the need for some fine-tuning is inevitable. Unlike surface traffic, on a rail system, you can't just drive around a slow train. With a 2-minute spacing of trains, even a small delay can ripple throughout the entire system. The usual cause of delays are passengers holding the doors open. If a train is delayed, the folks at transit control will override the signals on the line so the trains don't bunch up. The operators here can talk to the entire system, or the individual trains, passengers on the trains, passengers on the platforms, collector booths, or train crews. They keep the traffic flowing and the system operating. Here's something you didn't have to do with your little train set. Metal wheels get flat spots from slippage due to weather conditions and a variety of other things. Even a small flat spot on a wheel carrying that much weight gets very noisy. Flat spots are found during routine maintenance inspections. This is another accessory they don't sell at model train shops. In all those years of front window gazing, I guessed one thing right. The square tunnels were dug down from above, then covered up. The round ones were drilled without disturbing the area up top. A good example of this is the round tunnel underneath University Avenue. There are several hospitals above, and traffic couldn't be disturbed for construction. One day I'll be real rich and own my own train set like this. Wonder where I'll put it. You probably wouldn't think this was a good design for a bookshelf. It's amazing what the addition of one little nail will do to most people's perception of a design. In actual fact, this design is just as bad because it concentrates all the stress at that one spot. In designing a building or a bookcase, you have to take several things into account, most notably the characteristics of the materials and the fasteners and the force working against you. Rectangular long pieces of wood will bend this way, they bend less this way, and they'll take quite a load this way. The force working against you is gravity. gravity acts at right angles to any given spot on the Earth's surface. Now, see, I can get this stick to stand up if I can get it exactly perpendicular to a level surface. If I can get the gravity to act straight down along its length, it'll just stay there. Actually, I don't think the surface is level. Our director, Stu, built it.
You helped.
Now, as soon as I let gravity get a hold of the stick at any other angle, it just falls over. So geometrically speaking, that makes the right angle important to stability. The other geometrically important thing is the triangle. The problem with these joints in the bookcase is that the fasteners are expected to resist rotational force. They won't. In other words, nails are strong this way, but weak this way. Adding another stick here to form a triangle removes any possibility of rotation. But you don't want a triangular bookcase. How about this? One bookcase made out of two triangles. Now you can also get stability by putting a back on the bookcase, but don't make it out of thin strips of wood at right angles. As well as knowing the characteristics of the materials and the evil force of gravity, you have to take into account what effect gravity has on your materials. A wood shelf can't have too large a span or it'll bend. Now the obvious fix for this is a support in the middle. But where does this support get its support? Don't laugh, it's not a stupid example. My house is built like this. This kind of a construction is called post and lintel. Most houses in North America are built with post and lintel construction. One of the biggest problems in post and lintel is the big span. Now, there are various ways to stop materials from bending in the middle of a span. A lot of them involve triangles. Post and lintel isn't restricted to wood. The Greeks have been doing it in stone for quite some time now. See, the types of building materials that you find around the world depend on what's found in the area. For instance, there's a shortage of lumber stores in the Middle East. Something to do with the lack of trees or something like that. The Greeks and Romans loved to build with stones. Long spans of flat stone have similar problems to long spans of wood, with a couple of interesting differences. One, they're hard to lift into place. And instead of bending, they break, come crashing down. Long one-piece stones are also hard to find. The Romans increased the stone span by using curves. The curve is handy because it transfers its loads elsewhere. Part of that transfers down onto the posts that hold it up, but the other component is outwards. So the posts will need some sort of buttressing. Triangles are pretty great. Curves in architecture are called arches. If you play around with stones building arches, you notice that any arch you can build without having to glue the stones will have a place that you can draw a smooth curve on it. Arches that are extended in this direction are called vaults. The vault still needs the same kind of buttressing as the arch, but those pesky Romans were clever. Two vaults at right angles will buttress each other. This is called a groin vault. The logical extension of the groin vault is a dome. Dome is actually an arch that's been rotated through 360 degrees. The concrete that we build big buildings out of is a lot like stone. Concrete slabs will take compression quite well, but concrete won't bend or stretch. It breaks. Because of that, the concrete used in buildings is reinforced with steel rods. The placement of the rods isn't haphazard. Where the concrete slab will have a load downwards, the bottom of the slab will have stretch stress, so the rods are closer to the bottom. The reverse is also true. At the posts, the force is upwards, so your average concrete span has its rods embedded in it like this. Concrete's not great for punch-through either. That means that the posts either have to be made bigger than necessary, or the tops have to be flared outwards to spread the force. You can see this in most parking garages. The interesting thing is that you can sort of draw an arch here. Audience research shows that most people in our audience who build buildings already know most of this stuff. But there's no reason that the rest of us can't make use of the information. To get you started, Acme School has designed a stable, architecturally correct bookcase. Don't write in for the plans. It's a fairly simple matter to convert one channel to another. I had to say that during the cable item to move the story along, but conversion's pretty interesting. Converting one frequency or a group of frequency to another frequency relies on beats. Here's an audio tone. Here's another audio tone. When I get them close in frequency, a magical third tone results. One way of looking at this is that this frequency of 610 cycles per second has converted this frequency of 600 cycles per second to a new frequency of 10 cycles per second. In actual fact, we have a mess of 3 tones there, though. We have the 2 originals. To complete the conversion, we'd need filters to get rid of the 2 original tones and leave us only with the 10 cycles per second. All radio and TV tuners have used that principle long before cable TV ever came along. The tuner in an AM radio is actually tuned to 455 kilohertz. That's not a frequency that appears on the dial. And when you rotate the dial, you're actually changing the frequency of a local built-in oscillator that beats the incoming radio signals down to 455 kilohertz that the radio then tunes in. Doubting Thomases can do an experiment. Take 2 radios close together, turn one up, but not tune to a station. Take the other one, turn it on, but don't turn it up. As long as the radios are close together, you'll find that if you adjust the dial on the silent radio, you can tune in stations on the other radio. All radio and TV tuners use this principle. It's called superheterodyne. And the frequency internally that they're really tuned to is called the intermediate frequency. Now, originally there were scheduled to be 13 TV VHF stations, channel 1 through channel 13. But early TV was plagued with interference, and it was discovered that the new TV signals were beating with existing services and creating new beats that were right in the middle of the IF frequency they were using. To solve the problem, they removed channel 1 from TV service so they could move the IF frequency in the receiver just a little bit higher. That solved the problem. As to why they never relabeled the channels 1 through 12 instead of 2 through 13, nobody's talking.